Hello, this is one of a series of videos about solving first-order differential equations. And in this video, I'm going to be talking about a particular kind of first-order differential equation known as an exact equation. So we'll talk about what those are and how to solve them. And this is going to involve partial derivatives. Now, these are not partial differential equations. They are ordinary differential equations. But in the process of solving them, you're going to have to know what partial derivatives are and how they work. So if you need a quick refresher, if you have a function of more than one variable, like f is a function of both x and y, the partial derivative of f with respect to x, which could be written with these funny looking d's or with a subscript, basically you would just follow all the rules for finding the derivative of that function. And when you're following those rules, treat x as a variable and treat y or any other variable as a constant for the purpose of finding that partial derivative. Then when you're finding the partial derivative with respect to y, you treat y as the variable and x as a constant. And then the differential, the total differential of a function like that is defined to be its partial derivative with respect to x times dx plus its partial derivative with respect to y times dy. So for example, say f of x and y is the function x squared minus 5xy. The total differential would be the partial derivative with respect to x. So when we differentiate with respect to x, the derivative of x squared is 2x, and the derivative of minus 5xy, the minus 5y gets treated as a constant, and the derivative of a constant times x is just that constant. So that's why we got 2x minus 5y times dx. Then the partial derivative with respect to y would be, well, since x is treated as a constant, x squared is constant, and the derivative of a constant is 0, and then the derivative of a constant times y is that constant. So we get minus 5x times dy. So if we had this differential equation made up of 2x minus 5y times dx minus 5x times dy equals 0, the left side of that differential equation is really the total differential of some function f, in this case f being x squared minus 5xy. So the differential equation here says that the differential of f equals 0, so if we integrate both sides, the integral of df would just be f. And we would have f equal to c. That is, x squared minus 5x equals c. Or if you wanted to solve that for y, you would get that y equals x squared minus c over 5x. And that would give you the solution to that differential equation. So, given a differential equation of the form something times dx plus something times dy equals 0, the left side of that equation, made up of something times dx plus something times dy, might be the differential of some function. And if it is, then by taking the function that it's the differential of and setting it equal to an arbitrary constant c, that gives us the solution to that differential equation. And in a case like that, we call the equation an exact equation. So an exact equation is one where you've got the differential of some function equal to 0. Or equal to a constant, and if you had some constant over here other than 0, you could subtract it on both sides or do something like that to it. Now, how do we tell if a differential equation that's set up in that form fits that category? We can test whether it's an exact equation or not by checking to see whether the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. If so, it's an exact equation. And if not, it's not an exact equation. And the reason this works is because if it is an exact equation, that means that the thing in front of the dx is the partial of f with respect to x. So when you're taking its partial derivative with respect to y, what you would get would be the second mixed partial derivative, f sub xy. That is the partial derivative with respect to y of the partial derivative with respect to x of f. And when you're taking the partial of n with respect to x, you're really taking the partial with respect to x of the partial with respect to y of f. And these mixed partials, f sub xy and f sub yx, are supposed to be equal to one another, at least as long as conditions of continuity and differentiability are met. So here's an example. 2x plus y dx plus 3x minus 2y dy equals 0. Now it is set up in that form where we got something times dx plus something times dy equals 0. So is this an exact equation? Well, the partial derivative of m here with respect to y would be 1. And the partial derivative of n here with respect to x would be 3. And since those are not the same, this is not an exact equation. So if we were going to try to solve it, we'd have to use some other method. And I do notice that the coefficient functions here are both homogeneous of degree 1, so we could solve it using the technique that I talked about in a previous video, where you got homogeneous coefficients. Okay, what about if we've got 2x plus y dx plus x minus 2y dy equals 0? Is this exact? Well, here, the partial of m with respect to y is 1, and the partial of n here with respect to x is also 1. And since they are the same, this is exact. Okay, now what? If it is an exact equation, that means this is the total differential of some function of x and y, but we need to find what that function is. We need to find some function so that the partial of that function with respect to x is 2x plus y, and at the same time, the partial with respect to y of that same function is x minus 2y. Okay, so how do we do this? How do we find this function? Well, start from the partial of f with respect to x has to equal 2x plus y, and anti-differentiate with respect to x. If that's the derivative with respect to x, then the function it's the derivative of would have to be, the antiderivative of 2x would be x squared. We're treating y as a constant, and the antiderivative of a constant would be that constant times the variable. So we get xy. And then when we anti-differentiate, we add on a constant of integration. So we usually end with a plus c. But here, our constant of integration is only constant as far as x is concerned, but it might depend on y. We're really talking about partial derivatives with respect to x. So the constant term doesn't depend on x, but it could depend on y. So I've written it as g of y, something that's constant as far as x is concerned, but might be some function of y. Now from here, there's two ways we can go, two variations on how you get the rest of the way to the solution. One way to do it is to look at the second coefficient function and deal with it kind of the way we dealt with the first one. The partial of f with respect to y is x minus 2y, so let's anti-differentiate that with respect to y. If we do that, the antiderivative of the constant x would be x times y, minus the antiderivative of 2y would be y squared, and then plus something that is constant as far as y is concerned, but might depend on x. So I wrote that as h of x. So we've gotten two different expressions for this mystery function f. F is x squared plus xy plus something only involving y, but it's also xy minus y squared plus something involving x. So by comparing these, we should be able to get the complete picture. They both agree about what the part of the function is that involves both x and y should be. The first thing we got said there was an x squared in there. So that must be the term that only involves x. And the second thing we got said there was a minus y squared in there. So that must be the part that only involves y. And they both said we had an xy. So we would expect that to agree. So by comparing these, we know that our function of x and y has an x squared. That's the part that only involves x. It has an xy, and it has a minus y squared. That's the part that only involves y. And then we might have just a numerical constant that doesn't depend on x or y. So I could add on a plus c there. So there's the function, x squared plus xy minus y squared plus c, that has both of the partial derivatives that we want. So the solution to that differential equation that we were trying to solve turns out to be x squared plus xy minus y squared equals c. Now that isn't solved for y. I might not even be able to solve it for y, but it does implicitly define y as a function of x. So that's the solution to that differential equation. Now here's variation 2, a method that you might like better. So once you've gotten to this point, you've anti-differentiated with respect to x, take what you get there and partially differentiate that with respect to y. Find its partial derivative with respect to y. So the partial derivative of x squared would be 0. The partial derivative of xy would be x. And since g of y is something that just depends on y, its partial derivative with respect to y would just be its plain old derivative with respect to y, g prime of y. So that's the partial of f with respect to y. Now compare that with the in, the thing that was originally in front of the dy that was supposed to be the partial of f with respect to y. So x plus g prime of y must be the same thing as x minus 2y. The x's are the same, so the g prime of y must be the minus 2y, and then going backwards, anti-differentiating that, we get that g of y must be negative y squared, plus a numerical constant. So we can go back up here and fill that in for what g of y is. Now we know it's minus y squared, plus a constant. And we get our solution to the differential equation. We got f on one side, x squared plus xy minus y squared, equal to c on the other side. Okay, I'm going to end this video here since it's running a little long, but I'm going to follow this up with part 2 where I go through a couple more examples to make sure you got the hang of this.